we've already talked about sort of the administrative details and layering, correct? And I think I asked you a question last time. What was that question? Does anyone remember? At the end of the class, I asked you to think about something. Yeah.
Why do we both have MAC and IP address?
That's right. Why do we use have/use both MAC addresses and IP addresses on the current internet? Okay, that was the thing here. Okay, so I'll say something about that today. Okay, so I want to continue talking about something called internetworking. Okay, this is a little bit, this didn't happen. Okay, this is about how we forward data in the network. It says a little bit about how do we architect such networks. Okay, networks that are going to transmit information. Computer networks for which we use for transmitting or networking information. Okay, so we've seen this picture already. Just to remind you, you have edge devices, access links, network core, the core routers in the network. You have protocols, applications and services using protocols to communicate between edge devices. Right, so that's sort of the setup. The internet is inter means between, net, internetwork, so it's a network of networks. Okay. Yeah, so you have this mesh of interconnected routers that are going to be used to communicate information from two remote destinations. And the fundamental question is, how do you transfer this information through the network? Okay, and it turns out there are two broad approaches to transferring this information. One is called circuit switching. One is called packet switching. Now, circuit switching is so all transmission of information or communicating of information requires resources. Okay, so the main difference between circuit switching and packet switching is about the use of those resources. Now, do you buy my statement that communication takes resources? Like, what does that mean to you? This gentleman here with the gray shirt? Yeah, hi. What does that mean to you? Communication requires resources. But what does it mean to say it requires resources? Like, what does that mean to you? You said something about host. So you're saying you need like devices. Okay, so what else? Suppose now I have the device. What other resources do we require? What? Time. Okay, what else? Yeah, I hear bandwidth. What else? Yeah? Yeah, electricity or power. Yeah, exactly, right? So I think you're all on the right track. The point is, communication, computer networks, the devices require resources to carry out this function. And the basic question of how you transfer data is, are you going to use those resources? And the two broad ways of doing it are circuit switching, packet switching. Circuit switching is about resource reservation. Packet switching is about opportunistic use of resources. So at a very high level, that's the main difference. Actually, it's not a very high level. If you understand that, you understand the two. Everything else is actually detail. Okay? So circuit switching, you have a dedicated quote-unquote circuit. So they call it's circuit switching because it goes back to the early days of telephone networks. Right, when the company Bell, Alexander Graham Bell, telephone guy, the company that was providing, so one of the early names of the company providing these services was also Bell. They have the way they connected phone calls was there's a wire between the home and the exchange, and then they have to route, right, between different calls. And the way it was done was through a switch. And what you did was these switches closed circuits, which is why they call this circuit switching. Okay, but it's about dedicated or reserving resources for use during that communication activity. Packet switching is completely different. It says I have the same, now in both problems you have the same resources, but in packet switching you do opportunistic use of resources. So you don't get a resource that's reserved for you, you use it when you need it. That's the main difference. Okay, and these two are really different paradigms. Okay, in circuit switching, as I said, you have you reserve whatever resource you want. Link bandwidth, switch capacity, could be time. Generally, not power. Power is more of an individual resource. Okay, you might do allocation of power for services at a specific device. But from a system point of view, from a network point of view, it's not a system resource. Okay, so things like bandwidth, capacity, even time, right? And what happens is when you want to set up a connection, before you make the connection, you go and reserve all the resources. Okay, who remembers? No, so like, yeah, I mean these days it's not so apparent, but maybe 10, 20 years ago, if you picked up the phone and you dialed the number, there was a delay between when the call was connected and when you dialed. So what's happening in that delay? Right? It's not the time for the electrical signal to travel. It travels at speed of light, right? So it's not that. It's the resource reservation that's going on. So every let's say intermediate point that your call goes through, there's a request made. Hey, I want to connect this call. Can this intermediate resource, can you support my call? Yes, I move on to the next intermediate point, and so on. And the call doesn't get connected until everybody agrees to give you the resource you want. That's why when you make a phone call via like the landline, so the sort of the more technical name for the landline is public switch telephone network. When you make a call on the PSTN, it's pretty much guaranteed, right? That call is not going to get dropped. And the reason that call is not going to get dropped is all the resources along the route have been reserved. Okay, so that's circuit switching. So circuit switching, because it is based on resource reservation, gives you guarantees. Okay, it gives you, sort of a given quality of service, a guaranteed quality of service. Packet switching, on the other hand, as I said, is completely different. You do not reserve. It's solving the same problem, same resources, same problem, same connection that needs to be made. But you don't reserve resources along the way. What happens is you start your transmission, and you opportunistically get a resource from the first connection, and second connection, and so on. Okay? So clearly, packet switching doesn't give you guarantees, because it could be that an intermediate node or router cannot give you the resource. Okay? So packet switching does not give you guarantees, okay, in terms of latency, in terms of bandwidth. Okay, no guarantees. But what do you think it buys you? What does packet switching buy you? Can anyone guess? And the answer is not there. Just listen to me. What does packet switching buy you? What's the advantage? So the fact is, most modern networks are packet switching. So there must be an advantage. Sorry? Somebody said time. Yeah, utility of the link. Yeah, that's good. I think we are getting there. So the simplest example is when I was growing up, my sister and I used to fight for the remote control of the television. Who else has that experience? Or maybe you don't use TV anymore, right? These days you can watch everything online, right? But, television, one remote control. I used to fight with my sister about it, right? So let's look at, in that case, there's a resource. What is circuit switching? Circuit switching says, My sister gets the link from, 9 to 10 a.m. I get it 10 to 11 a.m. She gets it 11 to 12, and so on, right? We come up with a contract. We post it. We post a schedule. And when it's her time, I don't get to control the remote. So 9 to 10 a.m., right? She's gone off for a jog or something. Can I use the TV? I cannot, right? Because it's her schedule. That's circuit switching. Okay, but as soon as she comes back at 9:50, she wants to watch something for 10 minutes. She can do it, right? Because I can't use it. Because it's reserved for her. Packet switching says, because in our house we did packet switching. We were very visionary, We saw that everything was headed towards packet switching, so we were doing packet switching with the TV, with the remote control. It's whoever got there first, right? Whoever gets to the sofa first, where the remote is, right? But that also means that when she goes jogging, can I use it? Yeah, right? But it also means that if I'm using it and she comes back, she can't use it, right? So yeah, you don't get guarantees, but you get more efficient use of resources, right? That's what you meant, I think, by increasing utility, right? So packet switching gives you more efficient use of resources. Circuit switching gives you guarantees. Which one is better? So which one is better? Yeah, you're right, but keep it down. So hang on, I think you know the answer. So you guys in the back, which one is better? Okay, the 1, 2, 3, 4 of you in a row in the back row. Hi. Which one is better? Packet switching or circuit switching? Are you in my class? I don't know. People could just sit in the back and I wouldn't know. The 4 of you, hi. Can you wave your hand if you know I'm talking to you? Yeah, yep. Hands up. Hi, you too. Is your hand up? The lady there who's looking at me, Kim, do you see I'm talking? I see 3 people with their hands up. How come you're not putting your hand up? Are you? Oh, I see. You're hidden behind your computer. I can't see. So the 4 of you, tell me, which one's better? Packet switching or circuit switching? Do you know? A bit louder. I told you I can't hear you. You're going to make me come to you? You're not in my class. See? I'm not crazy. Are you sure are all 4 of you not in my class? Why are you here? You must have heard I was a really good lecturer, right? Okay, how about, I've now asked, are you in my class? You're also not in my class. So 1, 2, 3, 7 people not in my class. All right. Okay, if you're in my class, raise your hand, please. Wait, you're in my class. Okay. You are? I am in your class. But your friends are not? What? And are you her friend? Or you're not even her friend? This is like turning into a comedy routine, sorry. Okay, so you're in my class, good. So do you know which one's better? Actually, even if you're not in my class, you can answer. Packet switching versus circuit switching. Which one is better? Yeah. Yeah. So you said packet switching. What's your name? Spell it for me. eBay. Is it H? Do I pronounce the H or not? So say it again. Hebe. Who agrees with Hebe? She says packet switching. Okay, who doesn't agree with Hebe? Who says circuit switching? Huh? So is there a third option? I told you I was going to trick you, right? Remember, okay, I'm going to cut you some slack today, Hebe, and the rest of you. Right? Whenever I ask you if something is better, that's a trick question. Unless what? Unless I tell you how we're evaluating better. I didn't tell you, right? I gave you 2 facts. Circuit switching gives you guarantee. Packet switching gives you more efficient use of resources. Which one is better? It depends on what your metric is. You were going to say that, right? Yeah. Okay, so if you want guarantees, you have to use circuit switching, right? It's better. If you don't care about guarantees, but you care about more efficient use of resources, then packet switching is better. Right? So it really depends. That's why the public switch telephone network, the landline, is circuit switched still. And the internet is packet switched. Okay? Most modern networks are packet switched. Okay? So keep that in mind. Okay? Even your wireless is, so what wireless communication is circuit switched or packet switched? Like when you talk, when you make a phone call through the phone, function, not a WhatsApp call. That is circuit switched, but data services are packet switched. Okay, so the idea is to get a broad view of. This is a really important question. So if you're going to build a network, you've got to answer this question: how are you going to use resources? In a guaranteed way, in a reserved way, or in a packet switch way. Now, to let you know, technology has gotten really good. What used to be circuit switch services like voice, right? Voice is a constant bit rate type of service. You want guarantees. But yet, the majority of voice traffic now is on WhatsApp, FaceTime, Skype. It's packet switched. So technology has gotten really good. If you guys probably don't remember this, but if you tried to use Skype in the early days, it wasn't very good. But these days, it's virtually indistinguishable from a phone call, from a public switch telephone network phone call, or a cellular system phone call. Okay? So this is the main reason why services are going, or networks are going to packet switched. Okay? So another word for packet switching, the more general term, is statistical multiplexing. Okay, because what you're doing is you're randomly sort of using, randomly meaning opportunistically, as and when needed, allocating resources. You're multiplexing requests, but in a on-demand way. So it's called statistical multiplexing. Now, statistical so this is just an example of two computers trying to use a router. The router does things in a first in, first out manner. Right? So whoever gets the packet to the router buffer gets service first. Okay? And this is essentially statistical multiplexing. Statistical multiplexing is not just an idea, it's a very important idea. Okay? It's probably one of the main reasons. There's probably like 3 reasons you can talk about why the internet has succeeded. Why the internet works. Like people have thought internet is going to die. As you increase the load, it's just going to die. There's probably like 3 or 4 reasons. One of them has to do with layering, actually, what we talked about yesterday. Another reason is statistical multiplexing. And there's a couple of other reasons. Okay, but statistical multiplexing, to me, it's a very important idea. And it's a very powerful idea. Okay, so this is an example to show you how powerful it is. Okay, there's end users wanting to use a router, so you can replace the router by an access point or whatever, right? This could be Singtel, right? It could be an access point of Singtel. You have end users. Now, I'm going to give you a resource requirement. Each user requires 100 kilobits per second, but each user is active 10% of the time. Now, the router output link can support a rate of 1 megabit per second. Right? So in circuit switching, what you're going to do is you're going to assign 100 kilobit per second chunk to a user. You're going to assign it, okay, until they release it. Okay? So with a 1 megabit per second link and 100 kilobit per second required resource, how many users can I support? Crickets. How many users can I support? Come on. Huh? 10. Why? Yeah. So So it's 1 megabit per second divided by 100 kilobit per second, right? I mean, the answer's there. 10 users, right? But, okay, come. So remember, so still first week of me, so I'm going to cut you slack. But, we got to start getting, start interacting, okay? So circuit switching can support 10 users. Packet switching says I don't allocate a 100 kilobit per second chunk to any user. I give it to a user when the user wants it. Now remember, users are active 10% of the time. Does that make sense? That means they're not always transmitting, only 10% of the time. Okay? So I give a chunk to a user only when they want to transmit something. Right? And the question is, how many users can I support? Well, as I phrase it right now, it's not a well-defined question. You have to say, well, how many users can I support maybe with a certain quality of service? Because if I want 100% guarantee, how many users can I support? 10, right? That's circuit switching. With packet switching, I'm going to say, now if I just allow 10 users into my system, then I might as well do circuit switching. But the cool thing about packet switching is that I can allow 35 users into, so like I can allow more than 10 users. And as long as only up to 10 users are active at any given time, like I can support everybody, right? But the system will fail when there's more than 10 users, right? If there's 11 users, the system will fail. 11 users wanting service at the same time, the system will fail. So I can ask the question, if I have a bunch of users, in this case, in this example, I have 35 users, right? Like, what's the probability that the system will fail? It's just a probability that there's more than 10 active users at the same time. And it's kind of remarkable. With 35 users, the probability that 11 or more is active at the same time is less than 5 in 10,000. So that means out of 10,000 attempts to send the packet, 5 will fail. Do you think that's okay? Would you accept that quality of service? Yeah? Of course you would. And you would accept it even better because somebody's going to say no, right? There's always somebody in class who says no. I want 100% guarantee. So who's that person? Who will not accept any like less than 100% service? All of you will accept like 5 in 10,000? What about you? No, right? You're like, I'm paying for your service. I'm not going to accept any, drops or block in service, right? But what if I told you, I'll give you a 25% discount? Now would you? Right? I mean, I'll do my market research and find the number. So now think about it. I'm Singtel. With circuit switching, I can charge people, let's say, $50 a month. For 10 users, I get $500 a month. With packet switching, I can have, like in this case, 35 users at $50 a month. Let's say I have to give them a discount to have them accept the 5 in 10,000. So let's say half, 25%, 50%, right? That means I only charge you $25 a month. But 25 times 35 is more than 10 times 50, right? Because I more than double the number of users. So it's profitable. And the fact is you don't have to go to 50%, right? We are willing to accept like 5-10%. And we are very happy about it. And we are making the telcos rich. Because this is what they're doing. Guaranteed. Do you know who else does statistical multiplexing? Airlines. Do you know how airlines do it? They oversell seats, right? Because they know that some people will get caught in traffic, won't be able to make it. And an empty seat on an airline is lost revenue. So then you think, hey, but if you overbook, you have to pay somebody. They build that into the business model. That's the discount, right? That I told you, Singtel gives you a discount. They say, I have to take a hit. I have to pay somebody some money for them to take the next flight. But they built it. They're massively profiting. So airlines do it. Restaurants do it. Do you know how NUS does it? Can anybody guess how NUS or universities do statistical multiplexing? Yeah, they make more offers than places because they know that some people won't show up. So it's a very powerful idea. So it's not surprising that most modern networks are packet switch networks. Okay, so I think we understand the power of statistical multiplexing. So again, this is just about guarantees and efficiencies. Okay? So now I want to move a little bit to how do we, so what are the performance metrics in networks? Okay, so they are all the ones that you would expect, like loss and delay. These are the two main ones, right? Because they determine your rate or throughput. So throughput is also one of them, but it's a direct function of these two. Okay, and so I want to say a little bit about how delay and loss occur at an intermediate router. So you have a router there. You have packets, two edge devices sending packets into so this could be the access link, or it could be the core network, right? So what happens here? Packets are going to go into a buffer. Okay, right? So here packets go into a buffer and they wait for service, right? So they're buffered. The packet at the head of the queue is being served. When that packet is served, it's removed from the queue, and the next packet is started to serve. Now, depending on the relationship between the service rate and the arrival rate of packets, you can kind of understand stuff about this queue, whether the queue is stable or not stable, and so on. So I'm not worried about queuing analysis. I just want to get across that there's a whole set of delays. So what are those delays? All right, the other thing that can happen is if the buffer gets full, then packets get dropped, and that's the primary cause of loss. Okay, so the primary cause of loss in a computer network is intermediate buffers being full and packets getting dropped. Okay, we'll see later that sometimes core routers do preemptive dropping, right, as a sign of congestion. But it's also when the buffer is nearly full. Okay, but we'll just say right now losses happen when buffers are full. Delays happen because of the processing at the router. So there's basically four causes of delay. One is nodal processing. This is the node carrying out the protocol. You know, all the protocol stuff that we talked about, all the CRC checks and all that stuff, that's done by the core device, right? By the core router. So all that stuff takes time. The error control coding, the decoding, the CRC, the encoding, all that is the nodal processing. Then I told you that it's a FIFO queue, first in, first out, right? So packets have to wait for service. So there's a queuing delay. There's a transmission delay, right? Because there's a line with a certain rate. Packet has a certain size, so it takes time to transmit. That's called the transmission delay. And then there's a propagation delay through the line. Now, to be honest, this is speed of light, so it's usually negligible. But if you start having really long links, tens of kilometers, then this thing starts becoming non-negligible. But for all intents and purposes, it's very small. Okay, so you add all of these up, and this is the cause of delay through a network at an intermediate router. This doesn't take into account application delay at all, right? So that's an end-to-end thing. I'm talking about just at an intermediate node. Okay, so we've talked about, so you just add these all up. Okay, and as I said, packet loss is when a buffer is full and it cannot be supported by that buffer, so that packet gets chopped. What happens in that case is, so if I have an end-to-end connection, sender sending to intended destination, and an intermediate router drops the packet, what do you think happens? So let's say packet 4 gets dropped by this intermediate router. From this guy to the destination, packet 4 at an intermediate router gets dropped. What do you think happens? So think for a minute. This is an important question. We'll see if you can. So I'll give you a hint. You have to go back to the layered stack. And I told you what was the job of every single layer, right? Not with equations, but rather with like everyday language, conceptual, from an idea point of view. So which layer do you think kicks in? A bit louder. Transport, correct, because it's end-to-end. An intermediate router drops the packet, the transport layer protocol has to kick in and make sure that the sender retransmits that packet, because there's no state in the middle of the network. The intermediate router is not keeping state, okay? And none of the intermediate routers that up to that point are keeping state. The retransmission has to happen at the sender. So transport layer kicks in. Okay, so but losses happen, and of course that's how this affects your rate, right? Because I have to retransmit the packet. Okay, so that's packet loss. Okay, so let's take a look at some real delays and routes. I'm going to look at two. So some of you maybe already have experience with this. It's fine. Some of you may not. So I want to get everybody to the same page. All right. Okay, I'm on Windows. Usually I'm on my Mac. I think we can figure this out, hopefully. So you just open up a command prompt. Okay. The first thing we're going to do is I'm going to introduce you to a tool called ping. Ping is like a way of saying hello to a remote host. So if I do ping, let's see if NUS is configured to respond to ping. Yeah. So the web server that's hosting www.nus.edu.sg responds to ping. Okay. So this now notice that it also tells me what's the IP. I'm not sure. This is a DNS thing. I'm not sure why this is. I'm a bit perplexed. Okay, so because I told you yesterday that the IP address was 137.132, right? That was the NUS public IP. So this is a mystery to me. We'll figure it out. But you can see that DNS is telling you that this is redirected to this, to incapdns.net. So I'm not sure. I'm pretty sure this is not NUS's public IP. If you go to this thing should be wired. 45.60 is not private. Yeah, but let's go to if you go to, let's see, what is. See, now clearly 137.132 is not the public IP address of this computer, but this computer is going through the gateway, right? This is on an internal network. The internal network, you can call it VPN or private network, and if we actually looked at the IP address of this computer, I think a Windows is ipconfig, right? So the Ethernet adapter, so the IP address of this computer is this, 172.16.130.194. So 172 is a set of addresses reserved for intranets, for VPNs. Okay, the other one, there are basically three blocks of addresses, 172.192. And 10. Those are all reserved for private. So you won't find a computer on the internet with an IP address that starts with 172, 192, or 10. So the actual IP address of this computer is 172.16. Right? But what the world sees is 137.132.211.227. Okay, and this is essentially the IP address of the gateway. The way I leave the NUS private network is through a gateway, and this is the public IP of that gateway. Okay, So this is why I'm a little bit perplexed what this, when I ping NUS, I think that this has to do with DNS redirect. These things are always changing. I mean, I've done this before and seen 137.132. Okay, but so ping is a way of doing that. One of the things that you see is ping. You can make so ping here behaves differently than ping on Linux. Here you can give it a count. I guess you have to give it a count. So I could do ping minus yeah. So then, like if any packets gets dropped, it will keep statistics on what's been dropped and so on. There's a few other pieces of information that you see here. You see a time. So this is the round trip delay. So I'm pinging the server. I'm sending out a packet. The server is configured to respond to the packet. And this is the round trip time. It's 35 milliseconds. That's very short because that's on campus. Or, well, it's a bit long because I think of the DNS redirect. But if I made this, for example, someplace in the US, so this is Stanford University's web server, you should see the round trip time is much bigger now, right? It's 239 milliseconds. So it's an order of magnitude bigger, right? Because you got to go across the ocean. Okay. The other thing you see is a time to live field. When we talk about the network layer, we'll see what that means. It basically tells you how long can that packet hop around the network, like how many hops. It's not really a time; it's a number of hops. Okay. The other thing we can look at is traceroute. So what traceroute does is it tells you information about the path to the end host. So ping just sends a packet to the end host and waits for a response. Traceroute will give you information about the intermediate nodes. This is what traceroute does. So I have a thing here. So traceroute sends a packet to the first hop, second hop, and so on. Okay? And it basically, it will keep sending probes to all of the intermediate nodes here. Okay? So what I'm finding is, so here we go. So it's telling you about all the, so if you notice, we start going through a bunch of NUS intermediate routers. Eventually, we get to the border router. So this is the gateway. Now we're leaving NUS and probably going through some Singtel routers because Singtel is providing the service. Singtel is ISP providing access to NUS, but their routers are configured not to respond. So sometimes you get that the router does not respond. But you can see, right? The delay, if it's on campus, should be on the order of milliseconds, like 1 millisecond or so. When I did the ping, I saw it to be like 30 milliseconds, right? Which tells me it's being redirected out. So I think, unfortunately, this is... So what you can do is, and this is what I want everybody to do, you can do it on your own computer. If you have trouble, you can go to ping.eu. There's a very interesting... Somebody has set up a service, I think it's based in Germany. It's a service that allows you to run all these tools. Ping, traceroute, and a whole bunch of other tools. But it will run it from the server in Germany. So for example, if I do a traceroute, stanford.edu, from here, you will see that it will start going through, these are like European servers here. Okay, it's not, that connection is not happening from here, happening from the remote server. Okay, but I'll let you play with that. Okay. So in my notes, I give you an example from, this is when I did, okay, so I created this. So this is just pinging Yahoo. This is a traceroute from the Kuros and Ross book. I told you they make their graphics available. This is a traceroute, so this is what the output of a traceroute looks like. But again, I want you to do it yourself. Okay, so your task is to do it on your own laptop, ping and traceroute. Okay, the last thing I'll talk about quickly is throughput. Both delay and loss affect throughput, but throughput is also affected by the bottleneck link. Right? So in this case, you could think of throughput as a pipe that you're pumping water through. You're pumping data through. So clearly, if you have a sequence of pipes, the total information you can push through is limited by the smallest pipe. Right? The weakest link is the bottleneck. So that's all I'm trying to say here. So sometimes, if let's say you're at home and you're trying to surf some website and it's really slow, like most of you will probably blame your ISP, right? Damn Singtel, or whoever's giving you your access. But actually, it could be that the web server you're running from is some guy in his basement with a modem, right? And that's your bottleneck link. So it's not always Singtel's fault. It usually is, but not always. Okay, it could be the other side. All right, so I think what I want to do is I want to end here. I mean, if you look at this, this is just to figure out, just apply the idea of bottleneck link. The reason I'm rushing is I want you guys to do one more thing. Okay, if you go to Wireshark.org, so let me see. Yes, I mean that. So Wireshark is a tool for doing network analysis, for dissecting network packets and figuring out what's going on. Okay, we're going to use Wireshark in this class to try to understand a little bit about network protocols. So I want everybody to go here to Wireshark.org and install Wireshark. Okay, in next lecture, I'll say a little bit more about Wireshark, what it is, and we'll run Wireshark live, and we'll try to do some stuff and see how it can help us understand more about wireless networks. Okay, so any questions? So this is so the homework for you is to use ping and traceroute, either from your computer or ping.eu, and install Wireshark. Okay, in next class, we'll pick up with Wireshark. Thank you.